Welcome back to The Explainer. Today, we're taking a highly exclusive behind-the-scenes lab tour into a world you almost never get to see. I'm talking about the military's invisible battlefield. We're diving deep into electromagnetic testing, specifically a super-dense, incredibly rigorous standard known as MIL Standard 461G. I'm absolutely pumped to guide you through this, because honestly, what goes down in these testing labs is just mind-blowing. It's where raw, unadulterated electrical power meets meticulous engineering to make sure our defense systems actually survive when they're deployed. Okay, so let's kick things off by stepping back in time for a second to understand exactly why this standard even exists. The real catalyst here was a genuinely terrifying and tragic disaster back in 1967 aboard the USS Forrestal. Picture this. They're running combat maneuvers off the coast of Vietnam, and this invisible high-power radar signal from the aircraft carrier just sweeps across the deck. Well, that signal actually coupled with a poorly terminated cable shield on a staged aircraft. The induced current from that, it accidentally fired a Zuni rocket straight across a crowded deck. Literally one invisible spark triggered a massive chain of explosions. 161 injuries, and tragically, 134 lives lost. So yeah, it firmly established the absolute lethal stakes of what we're talking about today. Moving on to Section 1, the invisible threat.
So we really need to unpack what kind of invisible force could cause such a massive, catastrophic failure, and how modern military platforms are basically swimming in it. In simple terms, we're talking about electromagnetic interference, or EMI. Think of it as invisible electrical crosstalk. Modern military vehicles are easily some of the most electrically dense environments on the entire planet. I mean, they are packed to the brim with targeting subsystems, tactical radios, digital sensors, you name it. If these emissions aren't strictly controlled, these electronics will just unintentionally jam each other. Or worse, a simple, basic wire can suddenly decide to act like an unintended antenna, picking up powerful external signals and turning a vehicle's own wiring into a deadly, totally unpredictable hazard.
All right, Section 2, shielding the outside world.
So how exactly do we stop this from happening? Let's step into the physical testing space to see how engineers actually replicate and control these massive threats in a lab setting. When you walk into one of these testing facilities, the very first thing you'll notice is that the equipment is locked inside these massive heavy metal rooms called shielded enclosures. Now, I want you to think about this for a second. What is the actual practical purpose of locking military tech inside a giant metal box during a test?
Well, the most obvious answer is to prevent the external ambient environment from contaminating the incredibly delicate measurements happening inside. I mean, you literally can't accurately measure the faint, tiny electrical whispers of a military radio if your testing equipment is busy picking up the local FM radio station or civilian cell phone towers. But here's the thing. Blocking out that normal background noise, that's really only half the story.
The absolutely crucial point here is this wild reverse quarantine concept. These massive metal rooms actually exist to protect the outside world from the test itself. The signals getting generated inside these rooms are so incredibly, intensely powerful that if they weren't strictly contained, they would just completely wreak havoc on civilian infrastructure.
To give you a sense of the sheer, honestly dangerous scale we're dealing with here, just think about this number. 16,000 watts. And that perfectly illustrates just how extreme the military's testing environments really are. During these radiated susceptibility tests, engineers literally blast the equipment with up to 16,000 watts of pulse-modulated radar signals. They're using these massive power amplifiers and heavy-duty antennas to just crank out this intense electromagnetic field. It's a force that would easily destroy or severely disrupt nearby civilian tech, like your car's computer or local communication grids, if it wasn't heavily shielded to keep the neighborhood safe. Crazy, right? Which brings us to Section 3, building the virtual battlefield. See, engineers can't just slap a radio on a wooden table, turn it on, and blast it. They have to meticulously construct a virtual battlefield that perfectly mimics a real tank or an aircraft. It's almost like a highly specific recipe, layering the testing topology piece by piece. Step 1. Lay down a massive metallic ground plane, at least 2.25 square meters. Step 2. Elevate the technology exactly 5 centimeters off that surface using non-conductive blocks. And Step 3. Route all the interconnected cables in strict, mathematically arranged zigzags. So, why do these ultra-specific measurements matter so much? Well, that massive metallic ground plane isn't just serving as a table. It perfectly mimics the actual physical metal hull of a tactical vehicle, like an M1 Abrams tank.
By bolting the equipment directly to this plane, engineers can perfectly replicate how currents flow through a real chassis. Meanwhile, those exact 5-centimeter standoff blocks, they recreate the invisible ghost energy or stray electrical capacitance that naturally builds up when cables run right alongside metal vehicle walls. It essentially guarantees that the lab setup behaves exactly like a real-world deployment.
And consider the cable routing. You'd probably think they'd just coil the extra wire up nice and neat, right? Actually, no. The cabling has to be routed in a very careful zigzag configuration. If you coil a wire, you accidentally create an artificial induction loop, which is basically an electromagnet. By zigzagging the cables, engineers make sure they aren't accidentally inventing brand new interference that wouldn't even exist out in the field. Literally every single detail is controlled.
Okay, let's hit Section 4, probing for weaknesses. So, with our virtual battlefield built, we move right into the active testing phase. This is where the engineers go completely on the offensive. They forcefully probe the electronics to find absolutely any hidden weaknesses. The equipment has to endure an absolute barrage of simulated battlefield chaos. We're talking tests that perfectly replicate the severe shockwaves of indirect lightning strikes, the sweeping pulses of high-power early warning radar, massive voltage spikes from electrical switching, and the incredibly erratic, dirty power generated by heavy-duty military alternators. Now, to do this without just destroying the physical wires, they use a genuinely brilliant piece of engineering called a clamp-on current probe. Let's demystify that jargon for a second. Imagine a heavy metal donut that clamps entirely around a bundle of cables. Without ever cutting a single wire, it works kind of like a wireless phone charger, but instead of battery power, it inductively forces aggressive electronic noise directly into the cables. It's essentially injecting pure chaos straight into the system's nervous system just to see if the computer brains can actually handle the stress. During this specific test, which is known as bulk cable injection, there's a very specific numeric threshold that engineers forcefully push the equipment toward: 6 decibels. They don't just test this stuff to normal operating levels. The current is forcefully injected up to 6 decibels above the baseline calibration. Why go that far? Because out in the real world, low-level electromagnetic fields from nearby antennas can actually cause cables with the least electrical resistance to suddenly start acting like accidental antennas, pulling in massive amounts of energy. So pushing the test that extra 6 decibels basically guarantees that even under extreme, totally unpredictable conditions, the wiring won't carry destructive potentials directly into the subsystem processors.
And trust me, the hits just keep coming. Consider this massive electrical current used to simulate transient, split-second attacks, 10 amps. In one of these tests, engineers blast 10-amp damped sinusoidal transients. You can think of them as massive, sudden electrical tsunamis, directly into the interfaces. These are incredibly violent, split-second electrical pulses. They perfectly simulate the excitation of natural cable resonances that happen when, say, a nearby lightning strike hits, or when a massive piece of machinery on a tank suddenly switches on and revs its engine. If the digital processors don't crash or reboot during this brutal 10-amp shockwave, they are officially cleared for duty.
Finally, Section 5, winning the invisible war. Let's zoom out for a second to the broader implications here and what it actually takes to win this invisible war. When we compare MIL Standard 461G to your everyday commercial standards, there is a massive, massive gap in survivability. Industrial commercial standards are often, well, relatively benign, with relaxed, average-based limits. But the military standard? It features extremely severe low-frequency limits and incredibly heavy pulsed electric fields. We're talking about completely different operational universes here. And this presents a pretty huge challenge, because the Department of Defense absolutely loves buying commercial off-the-shelf equipment. I mean, it saves money and it deploys faster. But as we've just seen, commercial gear is incredibly fragile in these kinds of environments. It almost rarely survives this invisible military battlefield without some heavy, heavy custom engineering modifications, like specialized filters and super advanced grounding architectures, just to squeak by and pass these intense lab tests. Which leaves us with a pretty fascinating thought to wrap up the explainer today. Knowing about the massive radar pulses, the 10-amp lightning transients, and the heavily constrained environments we've just explored, if your beautifully designed, commercially standard smartphone was thrust into this invisible military battlefield, how many seconds do you honestly think it would survive before completely failing? It really makes you appreciate the hidden vulnerabilities of the devices sitting right in our own pockets and the truly incredible engineering required to protect the people who rely on military tech. Thank you so much for joining me on this deep dive, and keep asking the big questions.